So welcome back to this final lecture of this Swayam course titled Cornerstone Ideas in Material Science and Engineering. The intention of this course was to bring together pedagogy and content in a manner that is extremely rare to the best context of any engineering course for that matter, perhaps even science courses. So the way we chose to do that was by basically combining a micro session so to speak in pedagogy followed by some content, and typically the content would be covered using pedagogic techniques that have been discussed in the class and so on. In the last class we talked about a few aspects to do with primarily curriculum development, and we looked at very critical aspects of curriculum development. What we found when it comes to curriculum development is we should envision curriculum or visualize curriculum as a dynamical entity where there can be a distinction between the planned, delivered and experienced curriculum. However, what is critical is to sort of use the experienced curriculum to inform the planned curriculum. Alright, and over and above that we talked about the elements of curriculum design, and we sort of accepted that intrinsically it is an informed subjectivity oriented task. That means there is information, there is subjectivity in the choice that one makes in iterating one's curriculum. Nonetheless, it is informed subjectivity. So it is not arbitrary subjectivity under any consideration. There is information, there is experience that is embedded when you go through from one delivery cycle after another, when you update and refine your curriculum. Alright, and as parts of the curriculum design process, I mentioned to you about scoping and positioning. Very critical, by the way, because you wouldn't know the boundaries of the course if you did not scope the course appropriately. And also the connectivities with other areas so that the relevance of this particular course to other courses becomes very clear to the student. Then defining the course essentially, including the course objectives, the learning outcomes and so on and so on. Then detailed design. So you essentially have the skeleton of the course, which are, let us say, the objectives, but then what ensures those objectives? What are the activities, actions? What is the delivery plan? What will be the evaluative mechanism? What would be the formative assessment programs that you will have in place? So that would be essentially the detailed design. And then review and confirmation, essentially reviewing the design multiple times till you sort of are convinced that it's about the reasonable curriculum that you would like to actually work with. And this review process, by the way, is a very continuous process. I think it is very important for teachers to go into a course with an open mind, knowing fully well that they might have had some topical elements in mind, they might have had some structural elements in mind in the course, but then the students, for instance, through their interaction with one another and your interaction with them, it might actually be realized that some more elements may need to be added, some elements may need to be de-emphasized, some elements may need to be sort of overemphasized or emphasized even more to bring home relevance content and relevance associated with content, in fact. So that is what I mean by dynamic optimization, and then a refinement on the fly through various delivery cycles. Okay, so this is something that we discussed last time, and in fact to this bunch of students I asked them what the sources of subjectivity could be in their curriculum design, and they had some rather interesting responses. I mean, there are many sources of subjectivity. For instance, accessibility of the course can be a criteria and a constraint. Similarly, the level at which a course is offered can be a criteria and a constraint. You don't want to tone down the course, but at the same time you want to actually make the course accessible. So that sort of brings in design criteria, and that's really where the creative process and experience of the teacher can play a very big role. Also, it turns out that there can be other sources of subjectivity. For instance, the motivational spread in the class, the cognitive inclination and orientational spread in the class, also the level of preparedness, and perhaps also the various other kinds of divides between various learners in the class, their backgrounds and their prerequisites and the nature in which those prerequisites were pitched for them in their previous courses and so on. So all of these could add so many elements of subjectivity and n number of dimensions of subjectivity, but one of the solutions that was offered, in fact, by this particular class of students was you run a diagnostic test and at least see where the students are and give that feedback to the student and then give some informed reading accordingly so that the student can do some background work over and above what is covered in the class. Okay, so there is I think intrinsic value associated with that input that was given here. In fact, this is a well recognized practice among educators. So today we'll talk about topical choice, okay, and topic development, a very critical area because teachers very often have to develop content. When I had to offer this course, I had to develop content for this course, and sometimes you have to develop content from the scratch. It's a lot of structure that you need to put in place, a lot of eclectic resources that you might have to use in order to put something like this. And when I had to develop this particular course, there was no paradigm, there was no template on which I could actually stand. So the simple approach that I came up with, and I thought of it as an engineer would, to modularize it and to sort of integrate this into this. It's dovetailing it essentially, and that hopefully has worked out for those of you who are attending this particular course and so on. So the topical choices would essentially mean what are the cornerstone ideas in this particular course. You know, when we say cornerstone ideas in material science and engineering, what do you believe are the absolute foundational ideas in this vast, highly interdisciplinary, transdisciplinary area wherein there is an amalgamation, there is a fusion of many traditions from chemistry, from physics, from applied math, from mechanical engineering, from almost any engineering discipline that you can think of, including biotechnology, medicine even, dentistry, and so on. How do you actually teach something that is so eclectic? Okay, so one approach was sort of paradigm approach. For instance, we started talking about materials tetrahedron, how it helps inform thinkers about materials problems and projects, and so on and so on. So we can think about those paradigms and what are the concepts that form that paradigm. Alright, so curriculum are determined by relevance, necessity, preparation level of students. Now this is another variable in the equation. So when you take into account topical choices, where do the students come from? Okay, what is their background becomes rather important. And can you also make real world connect so that relevance would be a little bit more obvious, especially to a fresh entrant into the area. It is helpful to be also aware of the skill set that the student brings to the table. Now again, what happens is different students would be at different levels when it comes to a given skill, right? So there will be a spread associated with it, and it's rather important. Again, there some diagnostic tests would be helpful, and it is essential to also sort of in principle understand what the students' learning typically looks like. What do they understand by learning? What do they understand by the process of learning? Because these are very critical questions for the teacher, and it informs the way in which you sort of structure your course. You choose topics and cover the topics in a very specific manner. It underpins the philosophy behind which you make topical choices. Okay, so in all of this, the idea is to create a scaffold, and you have seen this word before. I have talked about Vygotsky's constructivism and scaffolding technique. The idea being that you create a scaffold around which the student sort of can rely on and add missing pieces to the puzzle that you are actually presenting. The puzzle here being the subject that you want to cover and the backbone of the subject that you want to cover, and so on. Now in all of these things, in addition to the content specific backbone, namely the scaffold that you want to cover, you should also keep in mind the student developmental aspects, and we have discussed this. So while on one hand we may want to support the student a great deal, it's also essential to remember that a challenge needs to be presented to the student too, because in the absence of that you will not necessarily ensure flow for the student. And autonomy, providing sufficient authority and autonomy to the student, freedom, intellectual freedom, cognitive freedom to the student becomes essential, and acknowledging the uniqueness of the students becomes essential. So we'll have to be very realistic when we lay out our intended learning outcomes. Extremely realistic in this particular regard. Okay. Now topic development. This is also rather important, because very often we find ourselves having to develop topics with very little resources at hand, and it might happen all the time, especially if it's a new course. You may have few resources at hand and so on. So it is rather helpful to be connected with learning communities. You know, perhaps if you're a teacher, it's good to be connected with other teachers who teach similar things. Learn from their experience, talk to them, find out what the major pitfalls were, what the major challenges were. Similarly, if it's a student, And especially if it's a student who would like to learn beyond the classroom, connecting him also or her also to learning communities that might be there in your area, etc., would be rather helpful. I'll give you an example of this in my research group, for instance, wherein there are a set of students who do computation and they are in certain fora, certain forums. For instance, some of them do computational modeling using ab initio technique. They are in the PWSCF forum. There are other forums that can be actually used as well. ResearchGate has similar forums for scholarly people and also for students who are pursuing MS, PhD. So that there are avenues outside and beyond the classroom for learning. So you provide opportunities for development in class, but also provide pointers for development beyond class. And your topics can be chosen such that there is some overlap between what is happening out there and what is happening in the class, so that the students see that there is a connect between learning in class and learning beyond class. You see the connect and you bring that connect to the class so that the topic might be suitably developed. Okay. The next term, which is very critical, is called course definition. Many people confuse the idea of curricular development with course definition. They are two different things in pedagogy. Course definition involves a statement or set of statements regarding the purpose of the course, which is the intended learning outcomes, the essential features of the course, and what the expected graduate profile looks like. For instance, a student who has taken course X will be able to do A, B, C, D, E, F, G. Okay, so that would be basically the course definition. So you define it based on the outcomes, intended learning outcomes, and what you expect the graduates to look like. Okay, what you expect the graduates to be able to do. And it also includes modalities. Okay, this is what you intend. How do you wish to set about doing it? What would be the modalities? Would it be a set of experiments? Would it be a set of theoretical discussions? Would it be a combination of the two? Would it involve some computation? So you can actually lay out the modalities also, so that the person who runs into your course definition understands, number one, what its aims and purposes are. Number two, what the student graduate, for example, is likely to look like, and how you aim at achieving it. The last topic for today's discussion, and after this I will essentially close, is internationalization of curriculum. And this is very important. In fact, it's going to be very essential in the Indian context as well. India is very soon opening up to be a global hub for education, and I think it is important for teachers and students alike to be ready for an international community of learning here in our own country. And students who come from different cultures obviously inherit different cultures of learning. And to ensure that there is a multicultural environment of learning and flourishing of the same is part of the aim of creating a curriculum that is sensitive to those requirements. So essentially providing multiple entry paths to people who come from different learning traditions. Okay, so that all of them somehow come on board, and that also goes into curricular design. So internationalization is in fact a very important aspect of curricular design. So I've taken this definition from this book, okay, and it's also there in the Teaching Learning Center, Flinders University's webpage. So this is a very interesting position paper, in fact. It is written by a few Australian scholars, so primarily focusing on education and changes in the educational landscape in Australia and how it impacts the economy of Australia, its impact on Australian industry, and as a consequence, what kind of transformation is expected in the university system, for instance, and so on and so on. And then if you are interested in reading further over and above and beyond what we have discussed in the class, there are some books that you might find on Creative Commons. So among the Creative Commons book, I am mentioning this primarily because they are free. So Creative Commons book, I have found this book to be very well written by Kelvin Seifert, who is actually a professor of educational psychology, and Rosemary Sutton. So both of them are in fact collaborators in their research endeavors, in their research projects. And there is this very nice book by Sage Publications called Communication and Instruction by Fawcett Warren. And this book, by the way, is not free and comes at a premium, but it would be nice if your libraries have it. It's a very nice coverage of some contemporary developments in teaching, learning and pedagogy. Okay, so I'll come back to this in a while, and now for now I will switch to content. Okay, so as far as recapping the content is concerned, in the last class we looked at the example of fractures in the case of mice, and we mentioned that fractures are extremely rare when it comes to small animals, and we found a reason for it. We in fact wrote down an equation. We found that the stress that you apply, the fracture stress that you apply multiplied by square root of c would be a constant, and this constant is essentially called the fracture toughness. And we found that the world's most tough ceramics, for instance, would have a few MPa meter power of half. That is the unit of this, okay. So this will have the unit of MPa meter power of half. But most of them would have just a fraction of MPa meter power of half fracture toughness. But in the case of bones, which are made up of a lot of calcium hydroxyapatite, you will find that this is in the ballpark of about 3 MPa meter power of half. And the reason why it is consistently high, by the way, this changes with respect to age of the person. It also has a dependence on various other factors, the hormone composition of the person and things of that sort. Typically, as the person ages, this goes down. Okay? And there are very interesting factors associated with it. We could think of it as a material science problem. Why is it that fracture toughness goes down? It has to do with the cellularity and connectivity, and the way in which calcium is sort of reinforced by living cells as a function of time. With the progression of age, how that is likely to change and so on. So there is a very interesting possibility of studying what happens to fracture toughness of bone, let us say, as a function of time. What we know for sure is in the case of human beings, as they grow old, it basically, the right hand side goes down as a function of time. They can retain it by interventions, but naturally left to themselves, it actually does reduce. It by and large explains why elderly people typically have fractures, and then there are challenges associated with the same, and so on and so on. Okay, not that it should be the fate of everybody, not that it should be your fate or mine. We can certainly intervene, as I said, to make sure that that right hand side is intact.
Can humans suffer fatigue failure in their bones within their lifetime?
All the time. Fatigue is basically cyclic load. So fatigue in the strictest sense, as defined by ASTM standard, requires you to apply cyclic loads, right? In the case of human beings, you can argue that there are periods of cyclic loads and then periods when there is no cyclic loads, and based on the part of the body that is being subjected to the stress. But you are right, there is fatigue. That is a definite possibility. There's no question about that. Fatigue does occur almost in any component that is structure, because you can actually look at this. For instance, now I'm walking, right? Now I stop. So when I was walking, you can actually consider it to be a cyclic load, because I'm applying some load here, then load here, and so on, right? So there you can actually think of it as many modes of failure, fatigue being one of the modes of failure, but impact typically results in fracture, and that tends to depend very sensitively on the right hand side, which clearly has a consequence of the constituents of bone, namely calcium hydroxyapatite, collagen, which is essentially a structural protein, and a lot of collagen. In fact collagen is the primary load bearing constituent in the case of bone, and then you have calcium hydroxyapatite, and then you have a lot of living cells responsible for the deposition of both calcium hydroxyapatite as well as fibers. Okay, and the fibers, you will notice, has some directionality about it. So that is why, let us say, this particular bone, it is more optimized for stress in this direction than in this direction, for obvious reasons. You would expect evolution to have done that. You would expect the fibers to basically run in this direction. You would have expected evolution to do that, right? And then in this context, we talked about cellularity, connectivity. We also looked at the example of syntactic foams and syntactic composites. And then we looked at composite classifications, namely metal matrix composites, fiber matrix composites, and then we can also think about ceramic matrix composites. We can think about dispersoids, things that you're putting inside these composites to strengthen the composites, for instance, or to add a new functionality. And there you could have things like, based on the dispersoid that you use, ceramic dispersed, fiber dispersed, fiber reinforced composite, and so on and so on. Increasingly, people are thinking about smart composites, composites that are not just structurally relevant, but relevant from some other point of view. For instance, because they give you an optical signal, they give you an electrical signal, an electrochemical signal, and so on, so on. So there is an increasing interest in something called smart composites. Okay, smart composites or smart materials. Typically, they are not just structural, they actually provide some functional properties. Electrical, optical, magnetic, electrochemical, electromagnetic functionalities are also there in them. Okay. Now, with that as the backdrop, we will think about ways in which we can make foams. So, you all know foams, right? Thermocol, for instance, is an example of foam. You know that, right? So, thermocol, it floats, it's primarily air, predominantly air, as much as 98 to 99% air. In fact, air is one of the phases in thermocol, and then you have an additional phase which is this polystyrene and so on. That particular thermocol is extremely lightweight, alright, extremely lightweight, and clearly has cellularity, and it has lots of holes in it, and so on and so on. So, how would you make it? Let us say that you have all the facilities in the world to make a foam. How would you make it? So please discuss this with one another. Come up with a few technologies that you can envision by which I can make foams. Okay, you understand the question? So you are welcome to come up with your own process. Take this, melt it, do this, do that. It's up to you. Don't be limited by equipment. Alright? You understand the question, right? So you are not limited by technology or equipment. You just have a sample of polymer, let us say, alright, and it is fairly stable, thermally doesn't degrade that easily or any such thing. You want to make foams out of it, how would you do that? Or a ceramic, you have some ceramic samples, you want to make foams out of it, how would you go about doing it? Yeah, you understand the question? You understand the question, right? So you have a polymer, in principle, let us say you can heat it beyond glass transparent temperature, no problem, it's chemically stable and all of that. Or a ceramic, you can heat it beyond melting point, no problem. How would you actually make a foam out of it? That's the question. So come up with 2 or 3 methods. Do you have an idea to begin with? Yeah.
Like what we do in case of metal, first we'll melt it and then blow the gas.
If it is metal, then blow the gas. Very good. Yeah, yeah. So what gas would you blow, and what will be the criteria for choosing those gases?
Argon.
Argon is a good choice. Why would argon be a good choice? Very inert gas. Fantastic. Very good. So argon is a good choice. He's right. Alright. Would you choose oxygen? No, because oxygen would oxidize the metal, isn't it? Many metals are oxyphilic. They oxidize, so you have to be careful. So argon is a much better choice. Instead, let us say you don't have argon. What are some of the choices you could think of? Nitrogen, very good, because dinitrogen is very, very stable. It's also an inert gas. In fact, nitrogen-nitrogen bond, it has a delta H of dissociation of about 950 kilojoules per mole approximately. That is very, very high, very high. So that's about 10 electron volts per triple bond. So to split dinitrogen, N2 to N dot plus N dot is very, very high, or N triple dot is very, very high. Okay, so that is a very good suggestion. So you could have argon, helium and so on, the various inert gases, or you could actually work with dinitrogen, and nitrogen is very cheap. That's an obvious advantage associated with nitrogen.
Another thing you can think of, like the excitive foaming, like we will add some particles.
You can add some particles. Yes, yes. Oh, okay. But then how would you get foams? Because you need air.
So what I think, if I take TiB2, so we'll add this particle into aluminum. As it is a foaming agent. So it will the cavities which are formed.
But that TiB2 cannot be a foaming agent. TiB2 actually comes apart, but it doesn't give rise to a gas.
So we'll add like a salt. It is like active heterogeneous nucleus. So there.
Yeah, so you can, the place where the foaming starts can be different from what causes the foaming, right? So what causes the foaming is, let us say, TiH4, which is typically what is used. So TiH4 decomposes at a few hundred degrees Celsius. So hydrogen comes out. Hydrogen has a very, very low, very, very large specific volume. So it's all bubbling out from all directions. And in the process, you start also cooling the metal foam, metal melt, and then you would actually have all these bubbles essentially frozen in, giving rise to a metal foam, right? That's a good idea, very, very good idea. Yeah, what are your suggestions? So they had 2 suggestions. One suggestion was you blow air, but certainly not with oxygen. You know, if you use synthetic air, you are in trouble because there is a possibility of oxidation of metal. So it's better to use some inert gas, and that inert gas can include nitrogen. And the reason why nitrogen is helpful is because dinitrogen is extremely stable, and it's also low cost, by the way. And instead of that, you could use hydrogen. helium, argon and so on, but of course you would have to pay the penalty of using those things. They are expensive, but they can be used. Nothing preventing you from using it. Of course, when you use one versus the other, the big difference is the diffusion coefficient. For instance, dinitrogen might diffuse very slowly through it, while if you look at helium, it might diffuse very fast. So the diffusion coefficients would be different, because helium is just one single atom. It's a very small, tiny atom, right? It's one of the tiniest atoms. Vis-a-vis, let us say, dinitrogen, which is a large molecule. So the process might be slower when you use dinitrogen. You might have to operate at higher temperatures when you use dinitrogen to get sufficient diffusion coefficients when compared to, let us say, helium and so on. So they said you could certainly think about blowing relevant gases. That could be dinitrogen or various inert gases. Another thing is, they said you can add some agents that decompose to give rise to gases having very large specific volume. So hydrogen has the highest specific volume. So let us think about something that is hydrogen evolving. So let us say TiH4 was one example, or TiH2. You heat it along with the melt at beyond a certain temperature. It basically comes apart and hydrogen evolves, and eventually that bubble that is created by hydrogen can be frozen in when you cool it down, right? So that was another idea that they gave. Do you have any other suggestions? Second one you thought, oh very good. So that is by and large what it is. So first one is called glass blowing, okay, and you can get huge pores on account of that. Can you see that, sir? From there you are able to see. That is called glass blowing, okay, can result in huge pores up to a few millimeters in characteristic dimension. This is because it's usually carried out on molten metals. Now this is important. Now gas blowing is typically carried out for metal foams, not for ceramic foams. This is a rather interesting distinction, and that has to do with the fact that ceramics at very high temperatures, especially beyond their melting point, can easily come apart. For instance, if you look at metal oxide beyond their melting point, which is usually very, 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 very high. So what you do is you usually add some impurities in order to make it easier for you to melt. And then if you sort of do this gas blowing through it, you might lose especially the cationic part. So there can be a lot of loss, lot of defects that adds a certain degree of complexity associated with ceramic foaming when compared to, let us say, metal foam creation. Okay. The other one is impregnation of an easily oxidized cheap material followed by air blowing. Now this is interesting, isn't it? So you have a material and that easily gets oxidized and becomes a gas. Let's say I impregnate something that very easily gets oxidized and becomes a gas. So I impregnate sulfur and then I do oxygen blowing. Sulfur becomes sulfur dioxide and escapes, leaving behind air gaps, right? And the last one is using agents that quickly decompose to give rise to gases. Right? So hydrides, for instance. What is the advantages about this process is that in principle it gives plenty of scope for introducing pores of a very, very large spectrum of lengths. You could play with the concentration of the higher of the foaming agent, you could play with the type of foaming agent, and you could go from let us say sub-micron size pores to several micron large pores to maybe in some cases millimeter size pores. So millimeter is rare, but you have tremendous flexibility when it comes to this. Okay. Now the next question is this, and I have written the answer also. Maybe you can add more to the answer. The question is, what material would you choose for the following application? The first one is heat sink. I have given the answer also. Read the answer and tell me whether I am right, or can I improve my answer further? Catalyst support is the next one, and thermal barriers is the next one. So note that ceramic foams have very low thermal conductivities when compared to metal foams. You would expect that, right? Because ceramic foams have mostly air and ceramics, and ceramic doesn't have the same thermal conductivity as metals. Now metals are champion thermal conductors. So if you have a metal foam versus ceramic foam with every other parameter kept constant, ceramic foam would be a fantastic thermal barrier. It would be a very good thermal insulator. And there is nothing, so why don't you discuss this with one another? Okay, so now you turn to one another. So there are three applications. One is heat sink, where I have to take away heat. Okay, the other one is catalyst support, and based on the kind of catalyst support based on the kind of catalyst you have in mind, you might have to choose support, right? And then thermal barriers is, let's say you have a space re-entry situation. The vehicle is entering the atmosphere again, and you want a lot of barrier to the heat that is generated because of friction. What would you do? Okay. So please discuss with one another. So why don't you discuss and maybe improve on the answer? Maybe the answer I have given is not good enough. Maybe you can improve it still further. Yeah. Correct. So that's right. Where you have a pore, you have air, and air is a poor is a poor conductor of heat. So between metal foam and metal will be a better conductor than metal foam. Between ceramic bulk versus ceramic foam would be a very, very, very poor conductor of heat. Yeah? Ceramic would be relatively better. Between metal and ceramic, metal would be usually much better. Though there are ceramics that are metallic. For instance, many nitrides are metallic. Titanium nitride, for instance, is a metal. So what are your thoughts? Can I listen to your thoughts? Yeah, metal foam allowed. As I told you, it depends upon the application. So it can be ceramic and metal foam. You are absolutely right.
So also, for example, the hydrogenation catalyst.
Yeah.
We are using
It's not hydrogenation. It is actually hydrogen evolution. Because hydrogen is not necessarily getting into the matrix. It's basically just evolving. So because when you say hydrogenation, it means I have a material and I'm putting hydrogen into the material, which is different from hydrogen evolution. Yeah. Yeah.
So we can make foams of those catalysts. We may not need extra catalysts.
Explain that idea again to me. I mean, what is it?
Hydrogenation reaction. Out of the catalyst, we are making
Okay, so catalyst itself you want to make it in foaming. That's a very good suggestion. Very good suggestion. No question. What about heat sinks? Yeah. The problem is most light metals typically are also highly oxyphilic. So look at the whole spectrum of light metals available, including aluminium. They're very oxyphilic, prone to oxidation, prone to all kinds of corrosion, etc. Here, the foamy equivalent might be slightly better, also because of the fact that you can work with something that is very stable, rendered in foam form, would be heavy in the bulk form, but that disadvantage is averted when you use a foam. So that's where that comes from. Okay? All right. So are there any questions associated with this? Any more questions? That's questionable, because what happens is, it's an interesting suggestion, provided you have enough cellularity in them and ideally a cellular face with sufficient connectivity. So you cannot just rely on metal foams, because what happens is you have this system that is just 1% metal essentially and mostly air. So if one part cracks up and there is very little structural support, the crack can actually propagate. So metal foams can be quite brittle. So there are metals that are not brittle, and metal foams, the corresponding metal foams can be very brittle. But you can avert it provided you have sufficient cellularity and structural support in the system. So the two keywords there would be cellularity and connectivity. So here is glass forming. A blowing agent is added, you will get glass foam. That's the answer. See, can you make foams out of glasses? The answer is yes. It's a special case of ceramic foam. So this could be, let us say, soda silicate glasses, for instance. So you melt it and then you add a blowing agent to it, for instance, and then out would come a glass foam. So it would be glass made up of glass, and at the same time it would be very foamy. Okay, so that's another thing I wanted to discuss. This is an interesting question. So read the 16th question. In a certain engineering application, I need a selective filter for gases. So I want it to allow, let us say, helium through, but I don't want it to allow carbon dioxide through. And typically, let us say, for this particular application, I have a mixture of helium and carbon dioxide. So what could I do so that I get helium out but not carbon dioxide? Can you discuss with one another? Pore size is a good answer. You can actually play with pore sizes. So you have this, so you can see that that's what I have mentioned. Start with nanoceramics, mix it with a thermosetting polymer, choose volume fraction so that ceramic particles will have enough connectivity, fire the mix to get rid of the polymer. Ceramic particles are connected to one another and they will remain. the pore size distribution can be carefully engineered so that one gas basically filters through while the other does not. And of course, there could be chemistries to it too. Yes, you could actually work with things that absorb and basically have higher diffusion coefficient through this particular ceramic scaffold, for instance. And so on. Alright, so let me go to this question. So this is an important question, just think about it. So, and this is true. If you look at research literature, you will find that if I have, let's say, two components A and B, I study the degradation of A and B versus the composite AB. Typically, the composite degrades faster than the independent components. Not always, but large number of cases where this happens. So, the composite tends to have higher fatigue. Okay, it tends to have larger amount of corrosion. The corrosion rate tends to be higher. And then the fracture also tends to be a very big problem. Slow fracture in particular, that is corrosion-induced fracture, tends to be more often seen in these composites. Why would this be the case? Can you discuss with one another? Come up with a reason for this, please. Do you understand the question? So typically, materials degradation is a challenge associated with composites. Why would that be the case? So materials degradation pathways could be fatigue because of cyclic loads or corrosion, including slow corrosion cracking, stress corrosion cracking it is called. In the case of a composite, why would that be the case? Alright. Yes. So what are your responses?
So one thing we can say about composites is that if we have a particular composite where the reinforcement is in the form of particles, particles with many different sizes, some of them might be having sharp corners or bends.
Oh, that's an interesting point. So curvature.
So they will be acting as centers of stress concentration. So whenever we apply a stress, which may be below the fracture limit.
So that's a very interesting point, right? So, and also those points can be places where a lot of electrochemical corrosion can also happen because it's a very sharp point. So that's a very, very interesting suggestion. So you basically have a matrix, and in the matrix you have these sharps, these dispersoids that are sharps, and so these could be regions where a lot of electrochemical corrosion and also stress concentration can actually occur, right? So that's an interesting point. For reasons to do with the fact that suppose you have, let us say, a structure like this, okay? So this is a pen, and at the tip of the pen you have very, very high curvature. And then let us say that it's the same material, this thing is the same material, but it's perfectly flat. So if an atom had to choose between sitting on the tip of the pen versus this, the atom would go there. It would rather go to a flat region than sit there. That is equivalent to saying that curved regions tend to have higher chemical potential. And hence they are very prone to corrosion. Okay? Yes. So, so you are also thinking in terms of structures, morphology of the dispersoid and so on. Okay. So let us look at the answer to the question. So composites contain interfaces. So you are right. They contain interfaces. There can be thermal stresses. Now let us say you put it through some thermal cycling. So you have a phase A, you have a phase B. This expands at a different rate. This expands at a different rate. Lot of thermal micro cracks can actually develop. If there are thermal micro cracks, oxygen can actually diffuse into it and cause corrosion. Also, these cracks could develop over time, could grow over time. Also, the interfacial bonding may or may not be significant. The interfaces may come off, right? And as a consequence, the shock resistance would be less. And it turns out that for reasons very similar to what you mentioned, see, look at the crack tips. I have mentioned that. They are called crack. So, you could actually have regions wherein there could be stress concentration, or which would simply by virtue of having high curvature be more prone to oxidation, more prone to corrosion and so on. So typically composites have so many more modes of failure than the independent phases, okay. So that is an interesting thing to keep in mind. Now here is another question. So a certain student argues that foams cannot be considered a composite. Well, she or he is wrong, right, because foams have a secondary phase, namely air, correct. As that particular question we have discussed. Now look at this question. you want to model or rationalize the properties of composites, how would you go about doing it? So what would be the parameters that go into the equation? So you want to model something. What do you think would be the parameters that goes into modeling the composites? Please discuss this with one another. To understand the question? So please discuss. So you write down the set of parameters that you think will reasonably make it to any computational model that you are likely to develop for rationalizing a certain given property. You name the property of composite. It could be thermal conductivity, it could be tensile modulus, it could be fracture toughness, name it. So we have discussed some parameters, which of those are likely to go into the equation and which of them are not likely to go into the equation. That's another way of thinking about it, okay? You understand the question?
So it is depend on which properties they use.
Correct.
So and the mole fraction.
So you name the property and write down the parameters. Whatever property, say you could think about tensile modulus or electrical conductivity or dielectric response. You choose the property. So what is the property you are choosing and what are the parameters? Choose any property, electrical conductivity, dielectric response, magnetic response, tensile modulus, you name it, whatever you want. And then say, okay, I expect it to depend on A, B, C, D parameters. So you have chosen electrical conductivity. Okay, electrical conductivity will depend upon individual conductivities. Will it depend upon the size distribution of the dispersoids or the volume fraction of the dispersoids? It will depend on the volume fraction of dispersoids. Would it depend upon the geometry of the dispersoids? Not just the volume, because if you look at resistance, for instance, correct. So shape certainly seems to make sense, right? Because for the whole bulk, of course, you could actually write it as rho. So, but rho would be some constant into rho A plus some other constant to rho B. Now, to a first order, this would be mole fractions, but it need not be, especially if you have a combination of very small nanoparticles and quantum dots and this and that, then that would change everything, right? So there will be, you will need to take into account some shape factors. Would you need to take into account some pore volumes and pore size distributions if there were pores, if it's a foam? Of course, that would be important. Would you need to take into account connectivities? Obviously, because it's a transport phenomena, connectivities will become important. Yes. Would you need to take into account anything else? Would you need to take into account the interfacial resistances of these based on the kind of bonding that exists and so on? So that would become important. So whatever lumped parameter you write should actually have a reflection of these parameters in it, right? What about you? What did you find? So this is one way to think about materials modeling. So the central challenge of materials modeling is, I want to describe this, what are the parameters I put in, and then what is the form of those parameters, what is the form in which those parameters come together. So think of it as a language where the parameters are the words, the constituting concepts, and then you structurally build it to give rise to a certain explanation, a paradigm for explanation and so on. So this is really the way to think about materials modeling. What is the emergent phenomena you want to explain, or what is the observed phenomena that you want to measure or explain? What is the measurable that you want to measure? In this particular case, it is the electrical conductivity. And then you ask physically, what are the parameters I expect that will go in? And then you can develop a line of attack, either to see how these parameters would fit in together. Sometimes dimensional analysis can be helpful when you actually fit those things together. Sometimes you have to use physical pictures and schematics and engineering models and so on and so on. Sometimes you can actually go down to the atomistic level, ask questions to do with bonding and things of that sort. And that is the program of something like multi-scale modeling, for instance, wherein you sort of abstract out parameters and think about ways in which you can explain properties, materials properties. What is the property you chose, and let us think about the parameters you have thought about. Mechanical. What mechanical property? Because mechanical elastic modulus. So you are thinking about Young's modulus. So rule of mixtures would be XA YA plus XB YB, correct? Where XA and XB would be the mole fractions. What is XA plus XB, by the way? 1. XA plus XB will be 1. So I can equivalently write it as XA YA plus 1 minus XA YB, isn't it? Alright. And that is because that is how mole fractions are defined, right? The mole fractions are defined such that the sum of mole fractions is 1. Okay. What is the next thing? So what are the material specific or dispersoid specific, matrix specific parameters that you will have to build in here, likely to have to build into this equation? So if it was a perfectly random matrix, then I understand. So you took into account volume fraction, okay. So instead of, I understand. So volume fraction makes sense. So you basically have, instead of mole fractions, volume fraction multiplied by Ya plus volume fraction multiplied by Yb. But again, somehow volume fractions would be 1, right? Okay. So that makes sense to me. Now the next question is, suppose you have new emergent phenomena. Suppose it's very analogous to the question of, can you treat them as two particles or two phases that are coming together without any interaction with one another? Once they start interacting with one another, clearly you will have to take into account interaction parameters, right? So for instance, you would have xa Ya plus xb Yb plus xa xb into something else, the dimension of Y, if they are interacting with one another. But if they are perfectly non-interacting with one another, then what you are writing down makes sense. Now, it turns out that that interaction can be chemical, it could also be strongly geometric, right? For instance, as you pointed out, what if you have spindles of one phase, okay, dispersed in the matrix vis-a-vis, let us say, spheres of this dispersoid in the matrix? You would have very different interactions. The spindles might interact very differently, especially the spindle tips might interact very differently with the matrix when compared to the spheres. Correct? So the interaction parameters become important where emergent phenomena is expected. This, by the way, you will see also in thermodynamics, isn't it? Wherein you have, let us say, enthalpy associated with a phase A, enthalpy associated with a phase B. The enthalpy of the mixture will be xa Ha plus xb Hb, where in this particular case xa and xb would be the mole fraction. But if they interact with one another, there will be an xa xb parameter, which is by the way called the regular solution interaction parameter. So you will see that in something like a materials thermodynamic course and so on. The same thing is actually seen, by the way, in electrical engineering too, wherein there is something called the Nordheim's rule. You know, it actually happens in the case of alloys. You can actually write it as xa rho A plus xb rho B, but if they very strongly interact with one another, and very often they do, especially metals do, then it basically you have an xa xb parameter, and that's called the Nordheim parameter. So there is something analogous to, let's say, students coming from electrical background understand that. There are analogies here, okay. So let us look at the note I have made here. Let us see. So some of the things that I expect are volume fractions, that you got it right. The shape and geometrical distribution, we discussed that, right. Next is nature of bonding, adhesive versus cohesive. By the way, cohesion is interaction between similar chemicals, chemical compounds or atoms and so on. Adhesion is between dissimilar ones. So that's what I have written there, adhesion versus cohesion. And then magnitude of interfacial area, very important. That is why I said that spindles can be different. Let us say if you have a composite made up of spindles versus composite wherein the dispersoid is spherical in nature, you would have very, very different results, okay. So the types of composites, there's something you have seen, isn't it? Metal matrix, polymer matrix, ceramic matrix. You have seen this, right? And then you can have structural composites and functional composites, correct? And then you can have composites based on dispersoid. For example, fiber reinforced concrete composites. So in civil engineering, for instance, the fiber reinforced concretes are basically examples of a composite. Large number of cements are actually examples of composite. When you add sand and gravel to cement, you essentially get a composite. Concretes are composites, okay. And you can have particulate composites. Particulate composites essentially means you have typically spherically charged particles that you are actually incorporating into it. And in all of these, the 3D connectivities of the particles becomes very important. And this we have seen, we saw a quintessential example of this in the context of syntactic forms, okay. Alright. So this is an example from ancient times, bricks with straw in it. You would have seen this in some archaeology programs in Discovery Channel and so on. They are actually composites, okay. Bricks with straw in it are composites. And the desirable features that are there in structural composites would be stiffness. Stiffness is essentially 1 over Y, the reciprocal of the Young's modulus. Toughness, you have already seen this. In fact, we have discussed fracture toughness in this class. Ambient and high temperature strength. Do these strengths need to be different? Obviously, they can be very different. And in fact, there is a parameter called creep, which we have discussed. In the context of polymer, there is something called viscoelasticity, and there are parallels between creep and viscoelasticity that we have discussed. So, structural composites, you expect them to be stiff and fairly tough based on the applications in my hand. And if they require to be operational at high temperatures, you expect them to be refractory. And as I told you, very often refractory composites are very challenging to get because this combination should be unreactive, and that is rather challenging. Okay. Now, this is a question that I asked you, I think, 1 or 2 classes ago. Why aren't alloys and ceramics considered composites? And the reason is because of the fact that in a composite, the polyphasic nature should not be compromised. It shouldn't be essentially becoming a single phase. Okay? So wherever you cannot sort of explicitly talk about it as a polyphasic system with a discernible volume fraction, you can sort of lump it either as an alloy or a ceramic, and you would not consider it to be a composite. Now please discuss with one another 2 or 3 lessons you have learnt about composites. Okay? And 2 or 3 lessons you have learnt about topical design. And with that, we'll come to the end of it, and I'll achieve closure to this class, and I'll make an announcement at the end of it. So please hold on. That announcement is important for those of you who are attending this course. So, things that you have learned as this composites is concerned, and things you have learned as this topic development design is concerned. So, have you written down for composites? What did you discuss? Yeah, so you can classify composites based on the matrices involved. So, fiber matrix composite, ceramic matrix composite, metal matrix composite. So, we learnt about composite classification in that context. You can also distinguish it between structural composite and functional composites. For instance, if it's a composite that is responsive to chemical stimulus, magnetic stimulus, electrical stimulus, then it would be a functional composite. On the other hand, if it is a composite that is meant primarily for structural application, then it would be a structural composite. Large number of composites are now being developed called smart composites, wherein they might be structurally relevant, but they are also smart. So, in fact, there are many companies that are involved in this particular area right now. So, another way in which you can classify composite is based on the dispersoid that is present in them. Correct? What else did you learn? The adhesion and cohesion between the dispersoid and the matrix matters a great deal. Very good. Next. Yeah, so what are the parameters that go into modeling of composites, isn't it? So you have to take into account the physics of the problem to actually model. For instance, if you are worried about, let us say, the degree of anisotropy that exists in the Young's modulus, then having a spindle shaped dispersoid would make a big difference as opposed to having a syntactic kind of structure, right? Connectivity would play an important role, and also cellularity could play an important role. The dimensions, the size, the geometries of the dispersoids would play an important role. Volume fractions would. The way in which they interact with one another would, right? What else? How to make foams. For instance, you could actually blow. So there is one way in which you can actually add something which oxidizes very easily, blow air into it, that would oxidize and escape, and it would leave a foam behind. On the other hand, you could do blowing of argon or nitrogen based on the situation, or other inert gases. Alternatively, you could also think about, so you could just do blowing directly. So you could do inert air blowing or air blowing, wherein you have a dispersion, you disperse something that oxidizes very quickly, or you could have some gas blowing agents, For instance, you could have titanium hydride, which splits to give rise to hydrogen. Very good. What else did you learn? So that is primarily what you learned. Let us scroll down and see. And then when do you call it a ceramic versus an alloy? When you have a discernible phase of the second, and both of them should be very clearly discernible, measurable, right? That is very important. And then we looked at applications of various foams, isn't it? We also looked at glass foam. You take molten glass, for instance, blow air into it, you would actually get glass foams. We looked at examples such as heat sinks, catalyst supports, and thermal barriers. We saw that thermal barriers, ceramic foams do a good job. Catalyst supports could be ceramic or metal based on the application at hand. Heat sinks, on the other hand, would be typically metallic forms, because metals would be very good conductors. And syntactic foam is something that you have seen in the past. This is a picture of that, right? And of course, in the last class, we discussed this. We started the discussion of composites by talking about bones and bone fractures, right? Good. Thank you very much. So that's a very good summary of the content part. As far as the pedagogy part is concerned, what did we discuss today? Yes. So, of course, we did a recap of what we have discussed in the last class, which is curricular design. Right? In the context of curricular design, we talked about how it's a dynamical process. We looked at this flow chart, planned versus delivered versus experienced curriculum. Then we talked about informed subjectivity in the context of curricular design. Then we talked about the phases of curricular design, scoping, positioning, definition, detailed design, review, confirmation, and finally refinement on the fly, right? And then we talked about topical choices. What did we learn about topical choices? Maybe this will be interesting to you. Relevance and connect to real world applications can be very helpful for students, isn't it? Then asking yourself questions to do with what the cornerstone ideas in the content are can be very relevant as you structure it. And also when you structure it, you can structure it in progression from simplest to the more complex. You can use the Bloom's taxonomy for the same. You all remember the Bloom's taxonomy, isn't it? And knowing about the students' learning schemas can be very relevant. Alright? So the whole idea is to scaffold the student through the learning process, isn't it? In all of this, we should take into account student development, and also connecting students to learning communities can actually enable learning even beyond the classroom. So these are some of the things that we discussed. We also looked at the definition of courses. So that is course definition, it is called. What it means, it is defined based on the graduate skills, based on the intended purposes, and the intrinsic coherence that exists in the course, and the increasing internationalization of curriculum, and why it is an absolute essential for Indian educators and educators around the world. Okay. So I also gave some instructions. Now this is an invitation to the teachers out there who have been with us through this course. So I would like to thank all of you for being on board throughout this course. It has been a rather interesting experience for me, and I hope it has been an interesting experience for all of you as well who have participated in this course in various ways, because we have tried to bring pedagogy and content together in a rather unique and what I think is rather interesting, productive and creative manner. So I sincerely hope it helps all of you and your students, and as a consequence that there is a ripple effect, there is a domino effect that comes out because of that. Now, I have always emphasized the importance of learner engagement. That means how, let us say, you could continue engagement with your learners. And in this particular context, I would like to extend an invitation to all of you who are out there. I would like to engage with you, and I know that the scale out there is huge, so it is very challenging to put this out as an offer, but I would like to put this out as an offer of engaging with you. And I'll tell you how I envision this. I envision this as a sort of a professional network that continues to discuss about topics that are of relevance to teaching and learning. This could be done through, let us say, Google discussion forums and so on and so on. And at the same time, this could also sort of be a space wherein like-minded people could come together to discuss education, research, maybe research in general, to better understand the Indian student population, to better understand one another, the institutions and the systems that we are part of, so that we can optimize better. And I think that there is value to continued engagement precisely because professions are built based on consistent, continuous engagement. It is not built on a pulse engagement. It is built on continuous, consistent engagement. So if I'm engaging with you right now, it cannot be a pulse engagement. It cannot be a transient phenomena. It has to be a rather continuous, consistent phenomena to make a difference. Difference the kind I hope to achieve and I envision. So in that context, I would like to put this offer out to you to engage with me both personally and perhaps through some forums that we could create on Google and beyond, wherein we could talk about topics that are of relevance to materials engineering in general, perhaps talk about topics that are at the interface of materials engineering and various other disciplines, chemistry, physics, biology, medicine, pharma, aerospace, it doesn't matter. basically explore those interfaces, because a lot of fertile territories are likely to open up between those interfaces, because there will be a lot of opportunities to ask questions that nobody else has asked, and hence opportunities to explore hopefully relevant and meaningful ideas in those spaces. So essentially a decentralized research approach is what I am actually envisioning here, okay? And while also becoming sort of more and more cognizant of where our students come from, so that we can provide a meaningful, purposeful engagement and learning experience to all of them. So with that, I would sign off, and I'm hoping to see all of you at some point in my life. I'm not sure how many of you I'll get to see, but if you see me in an airport or some such, do tap on my shoulder and say hello, and do tell me that you have seen me in this particular context, and I would be extremely happy. It could be anywhere, and all of you are welcome to come on IIT Madras campus to continue engagement with us. Thank you very much, and let me really wish you all the very best with all your professional endeavors, and wishing you the very best for making a difference to your students' lives. Thank you.